Yeah, so I hope my audio is uh, clear and you can see my screen as well. So yeah, we'll start. So today we'll be discussing about the important subtopic of your heat transfer course, which is natural convection. So, like as the name suggests, it's a natural or free convection. So it is a convection. So there will be a uh, conduction plus advection. So advection means there will be a movement of bulk of the fluid, but the difference is it's a natural flow. So what does it mean is there is no active pressure gradient that you impose. So it has its own physics is such that uh, a natural density difference is set up, and that results in the temperature difference, which causes the fluid to move in a particular direction, and that's why it is called as natural or free convection. So that should be the first thing that you should clarify. And apart from that, there are certain cases where you will not have an opportunity to actively push the fluid through. So in such cases, it naturally occurs, convection naturally occurs, and therefore, in some cases, it's very important. For example, cases where you are doing some condensation on a vertical wall or something like that. There you cannot always make the flow of air possible or with whatever is the fluid that you are studying. Sometimes it's naturally condensing, right? So there, wherever such condensing surfaces are there, natural convection is the predominant phenomena of heat transfer. So those things are there. Apart from that, there are certain things before, like we'll solve some problems, but before going there, you should know certain things about what you say about the governing equations. So basically, there will be you know boundary layer. So here, typically we deal with uh, hydrodynamic boundary layer and the thermal boundary layer. We generally don't study concentration boundary in case of natural convection, but you can. It's not like it doesn't exist. It will exist, but you have to uh, like the cases are very limited about that. So there will be a thermal boundary layer and there will be a what you say hydrodynamic boundary layer. So both of them will exist, and like what we did in our case of forced convection over a flat plate. You can write the governing equations. You can do the scaling analysis. All those things are still possible. However, I think due to interest of time, it was not covered in this course. But rest assured, you can do scaling analysis and all other things here. Typically, the most studied case in natural convection is a vertical flat plate, and there will be like some cases in which the plate will be hot and the ambient will be cold. Then there will be one type of boundary layer. Other case could be the ambient is hot and the plate is cold. Then there will be different type of boundary layer. So vertical flat plate is the most studied geometry in the natural convection domain, because in many applications you come across that. But that does not mean that it's the only geometry that is studied. Typically inclined plates, horizontal plate, then there are vertical cylinders, horizontal cylinders. All those things are there, but typically the vertical flat plate is the more involved case. It is similar to what we observed in our free force convection also. There also flat plate case is widely studied, horizontal flat plate. Whereas there will be certain other cases where we can have an inclined flat plate also in force convection, etc. But those cases are less studied, and you have empirical relations for them if you need. So like that only here also, uh, scaling, one can do the scaling. Uh, since we had not done it, I'll not go there. But there are certain important things such as Bosnick's approximation, etc., that you should be aware of. One second. Yeah, then there are like laminar turbulent cases also in natural convection. Sometimes people feel that uh, you know this in case of natural convection, flow will be always laminar. It's not like that. It can be turbulent also. That is decided by the Rayleigh number. Uh, you must have seen that Rayleigh number is a product of Grashof number and Prandtl number. So there are various things there, and if time was there, I think more things could be discussed. But uh, for the sake of this discussion, I just wanted to tell you that like it's not like natural convection is less important or like that. It is also very well studied thing, and if you are interested, you can always go and look into some in detailed discussions. But for the sake of this course, it's limited to certain cases, and we'll touch upon those only. So first of all is this governed equations. So as you know, uh, so about the governed equations, I'll just write them, but you know, for a vertical flat plate. So you know, this is a classical case where you assume that the plate is hot. So this will be your plate. This will be your plate temperature, which will be greater than the ambient temperature. This will be your ambient, and here it will be. They call it quiescent or stationary medium. Sometimes ideal medium. So here U infinity is zero, typically very small. And as done in the class, you assume this direction as y direction and this direction as x direction. So you have velocity component here and velocity component here, and you then solve your Govan equations, and then you come across something which is quite important. And here the fluid will, you know, what happens here the you know, near to the wall, the one second. This see, there will be a density gradient near to the boundary layer, and therefore the fluid will start moving down, right? Because uh, what happens, it's hot here and cold there, so density will be less here and more there. So yeah, let me just confirm once, because so yeah, we'll do that. But the main thing that I wanted to convey here was the uh, Bosnian approximation. Sometimes people don't appreciate that, because you know, it feels like it's like straightforward thing, but it's not. It actually helps to, you know, get rid of some non-linearity. You can solve the governed equations easily. So that is the case. So what it basically means is this. You know, you replace the so in this compressibility factor, which is defined as 1 by rho del rho by del t at constant p. You replace this what you say, del t by del rho by del t term as a difference of rho infinity minus rho and t infinity minus t. So this is the basic assumption, but what it does is it helps you, you know, simplify the equations. And how do you do that? Is basically, you know, we did it in the class, right? So, and sometimes, I mean, in this context, if you derive this way, it's different. But you know, Bosniak's approximation, essentially what it does, you know, See, what I mean is, one second. Yeah, what I mean is, in this Bosonics approximation, uh, they assume this thing also. What should I say? I don't want to confuse by giving another set of equations. That's why I'm not doing that. But maybe I have to do that. One second. We'll just. Yeah, so basically within this boundary layer, depending on your Prandtl number and all, which is out of the scope of this syllabus, typically you'll have a velocity profile like this, because the velocity will be zero at the free surface as well as your uh, your boundary, solid boundary, and you will have a temperature profile like this, because your wall temperature is higher, right? In this case, if it is the other case, it will be the other way around. So that was one thing. And coming to your your X momentum equation. Uh, so in the class we wrote it as so basically you get del u by del x plus v del u by del y, and there will be some uh, rho infinity minus rho by rho into g plus the second order velocity term. So this is your uh, solved, I mean simplified the whole equation, right? So what this Bosonics approximation says is, I should have written it earlier. One second. Yeah. So this should be the correct way to do this. And in the class we wrote it like this. I mean, in the class we wrote it like this, but when you look at this equation, what you observe is, you know, one second. So if I write it, it essentially means the change in density due to temperature change is important only for body force term. Okay, so essentially what it means is, uh, so there is some algebra involved here, because you can write your density as rho infinity plus del rho by del t at infinity into t minus t infinity plus some higher order terms. This is a Fourier expansion. And we all know the definition of beta, right, which I just wrote it here. So from there you can write this thing as beta infinity into rho infinity, and basically what I mean is I should just write beta, so like that. And therefore in the end what you get is rho infinity minus rho into g is nothing but your g beta rho infinity into t minus t infinity plus some higher order terms. And that means your what it means is linear variation in rho with respect to t by neglecting higher order terms. So this basically this is what the Boseniuk's approximation is, and what I'm trying to convey here is, and we use the same thing we used here. We did not put it like this, but we did use the same thing. We assume linear variation between the change in the density and change in the temperature, and that's how you solve the equations. So that was, I thought maybe we'll ponder upon that for some time. And then you do the scaling analysis and all those things. So I'll just give you some formulas before we go into the main thing. So basically there is something called as Richardson number. It is sometimes denoted by this, but typically you will observe this GR by RE square. So this is Reynolds number, Grashof number divided by square of Reynolds number. And if this ratio is significantly greater than 1, that means natural convection dominated flow. If it is significantly lower than 1, that means it is forced convection dominated flow. And if it is equal to 1, that means mixed flow. So there in mixed flow, your forced as well as natural convection will be significant. So sometimes this is also the important number that you should know, and you get this number from scaling analysis. You might have seen from class also. Sir also did the same thing. Yeah, and apart from that, yeah. So like, yeah, there is this Rayleigh number, typically denoted by RA. So if it is less than 10 to the power 9, it is laminar natural convection flow. If it is greater than 10 to the power 9, it is turbulent natural convection flow. This is for flat plate typically, but you can assume, like in some cases, you can assume it for cylinder also, depending on the characteristic dimension. Then, yeah, the thing is that we did not discuss anything about Rayleigh number. So, in case of laminar natural convection flow for a vertical flat plate, your Nusselt number is some constant into Rayleigh number power 1 by 4 and Prandtl number power 1 by 4. But this is when your Prandtl number is less than and your Nusselt number is equal to some constant into Rayleigh number power 1 by 4 for your Prandtl number value greater than 1, significantly higher than. These all things come from the scaling analysis. Okay, we did not discuss in the class because time is not there, but this constant will change, but the powers of Rayleigh number and all will be like that only. And I think for turbulent natural flow, typically your Nusselt number is scaled as Rayleigh number power 1 by 3. For Nusselt, I mean for turbulent flow, it's not that straightforward to do the scaling, but you can assume this typically 1/3 power variation for the turbulent flow. Yeah, so this was regarding the the things that I wanted to convey, and yeah, so again, Rayleigh number is the thing, but Grashof number into Prandtl number. We know Prandtl number is a ratio of two viscosities, or in other terms, it is mu Cp by K of fluid, and Grashof number is G beta rho G beta, no? Yeah. So rho G beta into Ts minus T infinity, which is delta T, characteristic length cube, and divided by the this kinematic viscosity square, and it signifies buoyancy force and viscous force. So you should know this much about this much definition about the this thing. And yeah, in this case also, this I mean this is for laminar case, but so it should be somewhere here. Your average Nusselt number is 4 by 3 of your local Nusselt number. So in case of laminar flat plate force convection, it was twice. It is here 1.33 times. And then there are empirical relations which are already given in the class, so you need to use them. And then there is boiling and all. We'll discuss them with the help of maybe some example later. So right now we'll solve some problems. So let's go there because I think the theory is already discussed. I just wanted to brief upon some topics which were not discussed. So yeah, we'll take first simple problem.
Hello, excuse me, sir. Hello,
Yeah.
sir.
Yeah, tell me.
Sir, in the previous equation, I think you have written rho excessively. Please check it, sir.
1 second. Where you are saying?
No, this last equation, Grashof number.
Yeah, what happened?
I think a rho is even be there, right? G beta delta T L cube by U square only, right?
Oh, acha. Okay. 1 second. Maybe I did a typo here. Yeah, let me just open the questions. I'll correct that. 1 second. Yeah, there should not be any row. Yeah, thank you for this. It's just a function of beta and rho here. Okay, so see, there is a typical type of, so like from the definition of Grashof number, so there is, see, we know this Grashof number is function of the G is typically constant, so basically, and yeah, so like if it is gas or air, typically beta is 1 by T in Kelvin. So whatever is your average temperature, you just take it in the Kelvin term, and you take the inverse, and you will get the compressibility factor that comes from your ideal gas equation. So I should write here ideal gas. Typically, if it is not also, we assume air as ideal gas. So like that. So but for liquids, it's not like that. Liquids, you cannot use this. And yeah, so here basically it is a function of delta T, characteristic length, and your fluid properties such as this beta, etc., and also G. So what I'll do, I can frame a lot of questions. For example, I mean, like question can be if for delta T of 20 degrees, your Grashof number was, let's say, 10 to the power 5. So what will be the Grashof number if delta T is 30 degrees Celsius, something like that. So what I'm implying is here I'll change one parameter and I'll ask what is the effect of that in the Grashof number. Similarly, if I put the vertical plate as horizontal or inclined, what happens? In inclined case, this G changes to G cos theta. So yeah, that's important thing. If plate is inclined by a certain angle theta, you have to replace by G cos theta because your gravity is not G there, that is G cos theta term along the surface of the plate. So like this, I just gave you the template. So I can frame like 4 or 5 questions here itself by changing each one parameter, fluid, temperature, all those things I can do, right? So that's what I wanted to convey. So here what will happen? You know that Grashof number is directly proportional to the delta T. So GR2 by GR1 will be delta T2 by delta T1, right? And by that logic, GR2 should be GR1 is 10 to the power 5 into delta T2 is 30 divided by 20 was the initial delta T. So basically it will be 1.5 to 10 to the power 5. So like that. I hope you get my point. So like that you are like small questions can be asked like that. So now you understood, right? And I can change the characteristic length. So for example, if it is a cylinder, if cylinder is vertical along its length axis, then its length is the characteristic dimension. If I use the same cylinder and I put it horizontally, in that case, what happens? You know, the diameter becomes the characteristic length. So like that, you can manipulate the questions based on those things. And then there is second template where what you do, you go one level up. So basically, you like change the parameter to get modified Grashof number, and you go one step further. What you do? What is the change in the Nusselt number? So like that. So if it is a laminar flow, we know that the Nusselt number is it scales as Rayleigh power 1/4 typically. Let's say Prandtl number we don't consider because it's a constant typically, and that means it is a GRPR power 1/4, right? So we know that Nusselt number typically scales as Grashof number power 1/4 in laminar flow flat plate. In some other geometries, they will give you the Nusselt number correlation, but you are expected to know about the flat plates, at least vertical flat plate. So in that case, what will happen? Same this question, this earlier version of this question. So here we got the Grashof number as this value, right? Then I can ask you what will be the new Nusselt number, given that the initial Nusselt number was, let's say, 100 or something like that. So this type of questions are there, and I think, I'm not going and I'm not making like 5-6 questions here because that's not the effective use of your time. But I hope you get my point as to what I'm trying to say here. This type of questions can be a good candidate for GATE exam, 1 mark question. Okay. So yeah, then we'll not do those objective questions much because either they will ask you some concept as to why does the why does the natural convection set up in natural convection boundary layer? What are the important body forces? So, for example, this Grashof number is it is a buoyancy force and viscous force scaling. So, like that, those type of questions are there theoretical, and then there will be a small category of questions like this where you'll change one parameter and you'll ask the effect on the Grashof number or Reynolds number or Rayleigh number or whatever it is. So, like that you can do. So now we'll take some conventional questions so that a lot of involvement in that. But typically there also it's not that difficult. So let's just take one question. So yeah, this is the previous year ESE question. So there is a horizontal cylinder in this case. So we are seeing the cross-sectional area and it is 1.5 centimeter diameter cylinder. It is lying horizontally. It is electrically heated. And it is in a quiescent medium, which is at T infinity is given as 315 Kelvin. Now it is mentioned that in order to maintain cylinder surface temperature. Oh, it's not cylinder actually. It's a sphere. My bad. Maintain sphere surface temperature at 385 Kelvin. Estimate heater. Estimate required heater power. So since the sphere is electrically heated, we need to estimate how much power we need to supply to the sphere so that its temperature is, maintained at 350 Kelvin. No, temperature of the surface is 385. The ambient temperature is, which is the ideal temperature, is 315 Kelvin. So we know since the sphere is hot, there will be some natural convection like this, right? And they have mentioned that. Okay, 1 second. So it will be symmetrical. Don't. I mean, forgive my drawing, but it should be symmetrical since it's a sphere. And the air will get heated and will start go like this. It will be rising like this, and like that you'll have a natural convection here. So now the question here should be, so yeah, see now somebody may get confused that whether it's a forced convection problem or natural convection problem. We discussed here, like we need to calculate the uh, this number, Richardson number, which is Grashof number by RE square, etc. Here you can calculate Grashof number, but they have not mentioned any U infinity or anything, right? So how do you calculate Reynolds number is the question. And before that, here I'll note down the properties that I have given. So yeah, so properties at 350 Kelvin are, these are given in the question. I'm just writing it down. The kinematic viscosity of the fluid is 2.076 into 10 to the power minus 5 meters square per second. Prandtl number is given as 0.697, so this is air basically. Thermal conductivity is 0.03 watt per meter square Kelvin. And your beta is 2.86 10 to the power minus 3 Kelvin power minus 1. And they have mentioned that use the Nusselt number correlation, which is given as, this is the average Nusselt number. This is 2 plus 0.43 Rayleigh number, which is based on your diameter power 1 by 4. So from here itself, you'll get the idea that this is a natural convection problem, since they have mentioned Rayleigh number in your Nusselt correlations. So now, first thing to solve any type of this type of problems is, since Rayleigh number is product of Grashof number and Prandtl number, first you need to find those. Prandtl number is given directly, so you need to find Grashof number. So Grashof number is G beta delta T into L cube. So here the dimension characteristic length is diameter of the sphere divided by square of your kinematic viscosity, fluid kinematic viscosity. So G will be 9.81, beta is given as 2.86 into 10 to the power minus 3. Delta T will be 385 minus 315. Correct, no? Yeah. And your diameter is 1.5 centimeter, so we need to take cube of that. So 1.5 into 10 to the power minus 2 cube. And the fluid viscosity is 2.076 into 10 to the power minus 5 whole square. Okay. So I'm skipping the calculation here, but you can cross check it always. It should be around 15,379.8. So basically it is around 10 to the power 5, roughly, like. So it is a laminar flow, that is one thing, but here we don't need to infer that information. So here we can now use the Nusselt number equation correlation. So Grashof number and Prandtl number. So you'll have 739.8 into 0.697 whole power 1 by 4. If you do that, you should get average Nusselt number as 6.375. And now we know that this will give you average heat transfer coefficient, and diameter is the characteristic length here. And if you put the values of diameter and conductivity, which are already given, so you'll get H as 12.75 watt per meter square Kelvin. Okay. But now what they have asked is we need to find the heater power. So heater power is nothing but HA delta T, right? So heater power is H average heater power, it will be delta T. Now for sphere, we know that the area will be 4 pi r square into delta T. So we know the diameter, so r is the half of that, and you can put all these values. Delta T will be again same as your Grashof number definition, and you should get Q as 0.631 watts. So this is your final answer. So I am not doing the calculations because I leave that up to you, and it will take a lot of time. So unnecessarily will waste our time. But if you are serious about it, you should all cross verify whatever I am giving you the answers. Here, before going further, you should take down one note that you know, the heat transfer coefficient order. What I mean is heat transfer coefficient for free convection will be typically less than heat transfer coefficient for forced convection, and that will be typically less than the phase change heat transfer coefficient. And I think you understand this, right? Because in free convection, the flow is primarily because of the density differences. There is no external pressure gradient. In force convection, you apply a external external pressure gradient in order to get higher heat transfer coefficient. And in phase change, since it's nearly isothermal process, the heat transfer coefficients are very high. So they are of the order of 10 to the power 4 to 10 to the power 5 in SI units. So because the delta T is pretty much low there. So this is also an important highlight because this here you got the H value which is around 12. So that is okay. That is okay. Less than 100 is fine. But let's say if you do some calculation mistake and you got this value as let's say 1000 or 12,000, then you should at least that should be a red flag, and you should at least cross verify your calculations once, and to just to be sure. So that is the purpose of giving this note. So like that. So next question we can take, so in natural convection, this type of questions are common. And the typical thing is you need to first find out the Grashof number, and everything starts after that. So we'll do one question. Yeah. So let's say this is another type of question. So it is mentioned that there is a flat plate like this. It's 2 meter is the height, 2 meter is the width. T infinity is 25 degrees Celsius. Surface temperature of the plate is 150 degrees Celsius. And we need to find first is heat transfer coefficient, and then you need to find rate of heat transfer. So typically those are the things that are asked, and we have given like other properties are given, which are your kinematic viscosity of the fluid. It's basically air. It is 1.6 into 10 to the power minus 5. Density is given as 0.972 kg per meter cube. Cp is 1.009 kilojoule per kg Kelvin. K is 3.13 into 10 to the power minus 2 watt per meter Kelvin. Since it's air, point Prandtl number is around 0.7. And they have mentioned that use the correlation as 0.15 into Grashof number. This thing. No, it's Rayleigh number, I think. Yeah, it's not Grashof, it's Rayleigh number power 1 by 3. So, see, this is the problem which is more or less similar to what we did earlier. Here, the only thing is your characteristic length is the length of the plate, vertical length of the plate, and area will be, instead of 4 pi r square, it will be the 2 into 2 4 meter square. Other than that, most of the things are same only, right? So as the methodology is considered, first you start with the Grashof number, which is G beta delta T L cube here, and this. So now here beta is not given, right, with the given properties, but we know that beta is 1 by T, so average temperature. So here average temperature will be 150 plus 25 divided by 2. But that will be in degrees Celsius, right? So what does it? What is it? So this will be average, and T average is 150 plus 25 by 2. That gives you 87.5 degrees Celsius, but we should put this in Kelvin because that is ideal gas equation, right? So this is 360.5 Kelvin, and if you divide it by 1, you'll get, you plug this value here, and therefore you get beta, which is 2.8 into 10 to the power minus 3 Kelvin inverse is the unit. And then you have put all these values in Grashof number formula. So your G is 9.81, beta is 2.8 into 10 to the power minus 3. Delta T will be 125 L cube. So this will be 2 cube divided by the kinematic viscosity of the fluid. 1.6 into 10 to the power minus 5 whole square. So if you do this calculation, you should get 1.06 into 10 to the power 11. So this is your Grashof number, which is pretty much okay. So we have this Prandtl number also, right, which is 0.697. So if you multiply that, you should get Rayleigh number, which is GRPR, as 0.74 into 10 to the power 11. This is greater than 10 to the power 9, right? So this is a turbulent flow. So this is just additional insight. It's not asked in the question, but you should get the idea. Okay. So now again, we know that it is given that your Nusselt number is 0.15 into Rayleigh power 1 by 3. See here the power is 1 by 3 because the flow is turbulent. I mean, if you don't know, maybe now you can get the idea. So put this number here and you should get your Nusselt number, which will be nothing but your HL by K. You should get this number as 627.59. Okay. Yeah, and now K is given in the question. Yes. So if you plug the value of K and L is 2 here, you should get H as 9.82 watt per meter square Kelvin. So this is your first part of the solution. And then heat transfer rate from the plate to the ambient will be HA delta T. So here you have to be careful because they have mentioned that the heat is being transferred from both the surfaces. So this is also area available for convective heat transfer, that is also there. So you have to take H, so you have 9.82. You have to take 2 into the area, which is 2 into 2, and into delta T, which is 125. So if you do that, you should get 9.82 kilowatt as your heat removal rate. I hope you got the point, right? In this type of problems, the methodology is first find the Grashof number, then get the Rayleigh number, then get the Nusselt number, then get H, and then get Q. So basically, if I want to summarize it in one line, first get a Grashof number, then get Rayleigh number, then get Nusselt number, then get H, and then get Q. So this type of problems are there where you directly you do the set methodology and you follow that. Let's say what else is there. Okay. So yeah, this is thoda tricky question, but it's not difficult. So here in the question, they have mentioned that there is a refrigerator, or let's say there is a wall at 30 degrees Celsius, and very close to the wall there is a this is your refrigerator surface. Okay, and the refrigerator surface is at 22 degrees Celsius, and it is 1.6 meters in height and 0.8 meters in width. So this is the dimension of the refrigerator surface which is facing the wall. And we need to find rate of heat gain by the refrigerator surface. So this is the case where your ambient is hot and your plate is cold. So there will be boundary layer which will be something like this in this case. You get my point, right? In other case, it was starting from the bottom and going up. Here it will be something like this. So you'll have some velocity inside like this. And here the temperature profile will be something like this, because your uh, sorry, your outer temperature will be higher outside the boundary layer. And you can assume the air is at 30 degrees Celsius. They have given the wall, but sometimes that is given to confuse you. And properties at T mean of 26 degrees Celsius are kinematic viscosity is given as 1.684 into 10 to the power minus 5 meters square per second. Thermal conductivity is 0.26 watt per meter Kelvin. They have given you alpha also, which is this thermal diffusion related diffusivity, right? So that is also 2.21 into 10 to the power minus 5 meters square per second. And they have given you Prandtl number also 0.7. So most likely it's air. And use the equation. This was given in the question only. For Nusselt number 0.42 into Rayleigh W is, I think, 1 second. Yeah, I mean, it's not required. So it's basically L, the length, power 1 by 4 into Prandtl power 0.012. So this is a strange power. Typically, it's not like that. And it is a multiply by the length into length divided by width of the plate raised to power 0.3 negative of that, minus 0.3. So this is some complex looking Nusselt number equation is given in the question. But again, we know, right, what is the methodology to solve this type of question. In this question, only the difference is they have not just given you the plate or something like that. They have given you a practical example of the refrigerator surface and the natural convection associated with that. So apart from that, everything other remains the same, right? So you have this. Yeah. So 1 second. Yeah, excuse me. So we know that Grashof number is g beta delta t here L cube by gamma square, right? The kinematic viscosity square. And we know that your Rayleigh number is GRPR, and PR we know, right? PR is basically your ratio of viscosity. So what I'm trying to say here is we can simplify our calculations and directly calculate GR as G beta delta T L cube. This remains as it is, and one uh, in the denominator you'll cancel one kinematic viscosity, and alpha will be from the Prandtl number. So this way you reduce your calculations, because otherwise you have to first calculate Grashof number, then Prandtl number, and then Rayleigh number. You can simply calculate it from here. So if you do that, you should get your Rayleigh number for your whole length of the plate or the height of the plate as 2.89 into 10 to the power 9. Okay, and now you put that in the result number correlation, so you get result number is in 0.42 into this Rayleigh number. Prandtl number is given as 0.7, and this is 1.6 by 0.8 raised to minus 0.3. So if you calculate all these numbers, and you should get around 878.75 as the result number. And we all know that this will be your HL by K. So if you simplify further, you'll get as 7.9, 12.79 watt per meter square Kelvin. So see, the solution is more or less mechanical, like what we did earlier. And here, HA delta T will be, you have to take the area of the plate. So the area is 1.6 into 0.8, and delta T is 8. Therefore, your heat rate of heat gain is by the refrigerator surface is 131.04 watt. So problem solving approach is just same, but the difference here is like here it is a different type of boundary layer, and the question was not as straightforward as it typically is. Okay. Yeah, so just a second, I'll drink some water. Then there is another type of question, not difficult, it's just that slightly different flavor, you can say. So in a room there is a sliding glass door. So there is a glass door of rectangular cross-sectional area in a room like this. The width is 1 meter, and the height is around 1.8 meters. This is your glass door of a room, and in winter the glass door temperature is 0 degrees Celsius, and the inside the room, inside sorry inside the room the temperature is 25 degrees Celsius. Oh, sorry, 50 degrees Celsius. 25 will be too hot in winter like this. Okay. And we need to find, first is the same thing, the heat loss rate from window. Not window, this is a door, sorry. Heat loss rate through the door due to convection. So this is a typical question that is asked, but the additional thing that is asked in this question, if room is provided with an electric heater, estimate daily cost of door heat loss for electricity cost of rupees 5 per kilowatt hour. So there is some cost angle also involved in this case, and they are given the properties at 280 Kelvin or kinematic viscosity is given as 14.11 into 10 to the power minus 6 meter squares per second. Thermal conductivity of the fluid is 0.0247. By the looks of it, it looks like air only. Alpha is given as 1.986 into 10 to the power minus 6. Oh, sorry, minus 5. Total number is 0.710. And use following correlation for Nusselt number, which is, so this is your HL, so this is your Nusselt number correlation for the whole length of the plate. So when you see this type of correlations, it's more or less, given that these are obtained by doing some curve fitting to some experimental data. And the whole thing is again squared, so yeah, like that. So now, first part of the question you can, you can solve typically like that only. Here again, we don't know the beta, right? Beta will be 1 by T average. They have mentioned T average as 280 Kelvin, so you can directly take 280. And if you do that, one second. Yeah, so 1 divided by 280. Sorry. Yeah, 1 divided by 280. That is 3.6 into 10 to the power minus 3. Inverse of temperature should be a scale unit. And now since we need Rayleigh number, again the trick that we used in the last problem, no need to calculate Grashof number separately. You can use this formula for Rayleigh number, right? So it will be G beta delta T L cube by kinematic viscosity into thermal diffusivity. So all the things are known now, beta is also known. So if you put those things here, you should get Rayleigh number for your whole plate length as 1.09 into 10 to the power 10. Okay. Now you have to use the Nusselt number correlation, which is a pretty scary looking one. So yeah, 1 second. Yeah. So if you do this TDS calculation, I am skipping it because it's quite involved. I mean, you can do it separately, but at the end of the day, that calculation you should get uh, the Nusselt number as 259.29, and then when you do the final substitution to get your H value, you should get the heat transfer coefficient as 3.558. And then what is your heat transfer loss due to the natural convection is heat transfer into area into delta T. Area is known, delta T is known. So you should get 96.07 watt as your rate of heat loss. So that is your answer to the first part, right? But now they have asked something else also. So they have asked to estimate the cost. So daily electricity I mean per unit cost is 5 rupees per unit kilowatt hour, and now we have to estimate the daily cost. So what is going on here is this is the energy lost per second. So first we need to find out how much energy is lost per day. So Q for a day, which involves 24 hours. So that will be 96.07 into 24 hours into 1 hour has 3600 seconds. So 96.07 into 24 hours into 3600. So that comes out to be 8300.45 kilojoule. So in 24 hours, this much heat is lost to the surroundings through the glass door. And now heater has to supply this much heat, right, in order to maintain the room temperature as 50 degrees Celsius. So yeah, so now we know that 1 kilowatt hour is nothing but 3600 kilojoule. This is the standard result. You should remember this. Or sometimes they call 3.6 megajoule. In refrigeration, you study this. In the course of refrigeration also it is important. So this 1 kilowatt hour corresponds to 5 rupees, right? So we need to find out how much cost is involved for this much of energy loss. So you can do the calculation, right? So daily electricity cost for heater will be 5 into 8300.45 divided by 3600. Okay, so yeah, so 5 into 8300, sorry, 8300.45 divided by 3600. So basically 11.53 rupees. So this much a person has to spend daily in order to maintain your room temperature at 50 degrees Celsius while your door temperature is 0 degrees Celsius, and you need to pay this much for the heater electricity bill per day. So monthly it will be around 330 rupees or something like that. So this was one of the problems that I thought maybe have some additional you know things involved. So yeah, so now we have covered mostly the natural convection problems. Apart from that, sir has covered boiling also, right? In 2 lectures. So in boiling, see, boiling or any phase change for that matter, boiling, condensation, etc. Uh, you know, they are very difficult phenomena to analyze using analytical methods, because phase change itself is a complicated method, and to study them or to get the general analytical solution for various geometries, etc., for various flow regimes, it's pretty difficult. It's possible with some assumptions, certain assumptions are there, but difficult. So, yeah, so there is important point of this boiling curve. You should study those various regimes. First is your pool boiling regime, where you have initially free convection. Then you have nucleate boiling. There also two regimes are there. Initially, there will be lesser number of bubbles, and towards the end of the pool boiling or nucleate boiling, the number of bubbles will increase rapidly. And after a point, there will be a transition zone where alternately on the surface of your heating wire, alternately water and vapor will be there. So that is your transition region. Then you'll arrive at a Leiden-Frost point. Then again, after that, if you keep on increasing your delta T, or the temperature difference between saturation temperature and your current fluid temperature, you'll end up in a film boiling region, where whole of your heating coil will be covered in a vapor, covered by the vapor. And what about the variation of H with respect to delta T in all those regimes? So this was covered in the class also, but for the sake of revision, at least you should uh, remember it like this. And remember that this boiling curve is valid for atmospheric pressures. Uh, if the atmospheric pressure is not 1 atmosphere, there may be a slight variation in the curves. So let's say you study both of them together only. So this is your heat flux, surface heat flux related to versus delta T plot. Delta T is your T minus T sat, saturation temperature, and what is the superheat degree that you are implying. And you'll have certain so you'll have certain maxima here, and you'll enter into transition zone, and then again you'll end up in the the film boiling origin. So let me just choose another. Okay. I'll maybe take a different color here. Yeah. Sorry. Yeah. So. Where? Right. I want them to. Okay. Yeah. I think this is better way to do that. Yeah. 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 There will be like a couple of regimes here also. So this is the region of your pool boiling. And this is the region of your transition. And then you go to the film boiling regime. Here you'll have free convection in the first. Then you'll have nucleate boiling here. And this will be your Leidenfrost point. Sometimes they ask, so basically you want to avoid this point, is what I would say. And sometimes what they do here, after achieving the maximum heat flux for your case, when it starts to go down, they don't maintain constant temperature for the heating wire. They just make it a constant flux condition so that you avoid the uh, you avoid the Leidenfrost point, and without loss of much energy they arrive there. But if you don't know this, that is also fine, because that is just a practical trick. But you should know. Sometimes they give boiling curve as like this also. But the black line is the main thing, is what I'm trying to say. And like related to that, what I'm trying to imply here is, if you plot the H versus delta T, which is your heat transfer coefficient versus your delta T, what happens in this region, your H increases, but in this region it starts to decrease. So there will be a maxima here somewhere for your H. So the point is, initially H will increase like this. It will attain maximum, which is not the maximum heat flux, okay? And it will start decreasing then, and it will again be obtain minima at your Leidenfrost point, and then again start increasing linearly. More or less linearly, not like exactly linearly, but like that. Okay. So the point here I want to make is your H value will decrease, like at Leidenfrost point, your flux will be also less and H will be also less. But when you have like maximum flux, you will not have maximum H. You will have maximum H somewhere before that point. Okay. So this is one thing you should remember. Maybe you can refer this diagram while revision, and you should be good. So this is your H max point. Okay. So like that. That is the difference that you should remember. Apart from that, maybe we can look into the type of problem, because see, there are these type of questions are all, like correlation based. You cannot you know derive general solution for them. So maybe today we'll take one problem. Let's say your assignment problem only, and we'll see what happens. So I think there are two problems on your boiling there. Uh, we'll take one of them. So let's say we'll take the fifth problem, the last one. So estimate the nucleate pool boiling heat transfer coefficient for water under atmospheric pressure. Yeah, so see here they have mentioned that it is atmospheric pressure. So typically, if not mentioned, you assume that, but whatever we study boiling, etc., we assume atmospheric pressure. There are certain applications such as boilers, etc., where the pressure may not be atmospheric. So accordingly, the properties and the correlations will change. So there is, okay, I'll note down what is the given. So this is your fifth problem in your assignment. So in this problem, they have given you the excess temperature. So that is your delta T of 15 degrees Celsius. And apart from that, they have mentioned that the pressure is atmospheric. So that is also there. I don't know whether it is important information or not for problem solving, but it's otherwise important information. And it is a water and stainless steel combination. And for this combination, they have given the surface constant as 0.013. Okay. And now other properties such as saturation temperature as given as 100 degrees Celsius. Density of liquid is given as 957.9 kg per meter cube. Density of vapor is 0.596 kg per meter cube. CP liquid, it's water, so it will be 4.2. So joule per kg Kelvin. Mu L, viscosity of liquid, 279 into 10 to the power minus 9 minus 6 minus per meter square, standard SI units. Prandtl number for the liquid is 1.76. Surface tension coefficient is 58.9 into 10 to the power minus 3 Newton per meter. HFG is 2257 kilojoule per kg. And this another constant is equal to 1. And they have mentioned that use Rosenhoff correlation. So Yeah, so it is flux as mu L HFG. See, here we are using this HFG directly because they have not mentioned any correction to it. But typically, this HFG is given at 100 degrees Celsius saturation pressure, right? Here we have excess 50 degrees Celsius. So actual HFG will be slightly other than or different than this value. Sometimes in question it is given that instead of using this HFG, use some additional factor of HFG and you get the actual HFG at this delta T. Here it is not mentioned, so we'll use HFG directly. Let's see what happens. Then this bracket is there. This is your bond number kind of scale. Sigma, so surface tension effects are counted in this term. And then you have this Jacob number kind of term, which is sensible heat, Cp delta T by your HFG, latent heat contribution. HFG into liquid Prandtl number power n. The whole thing is raised to the cubic power. And we know that this is nothing but H delta T, right? Because it's a flux, so it will be H into delta T. And that this is our purpose. We need to find H. Yeah, so I have not mentioned that, right? So we need to find. Oh, sorry. Yeah, we need to find H. So basically, what is your heat transfer coefficient during nucleic boiling heat transfer for this set of properties and conditions. So let's go with the Rosenhau correlation. So you have UL given as 279 into 10 to the power minus 6. All SI units are there, that's good. HFG will be 2257 into 10 to the power 3. The bracket will have 9.8 into rho L minus rho V. So that will be 957.9 minus 0.596 divided by the surface heat transfer, surface tension coefficient. Whole thing is under the root, and you'll have another bracket for Jacob number representative. CPL is 4217 into delta T is 15 divided by CSF is 0.013. HFG is 225 into 10 to the power 3. Prandtl number is given as 1.76 raised to n. N is 1. So it is 1.76 only, whole raised to cube. So now we'll find out the first term first. So this is 279 into 2257, and whole thing will be divided by 1000. So therefore this term will be 629.703. Okay. Now the second term. So yeah, this is 957.9 minus 0.596 into 9.8, which is your G, divided by, yeah, let's say into 1000 we'll do here only, and then we'll divide by 58.9, and now we have to take the root of this. So that is 399.099. Okay, and the last term, which will be 4217 into 15 divided by 0.013 divided by 2257 divided by 1000 divided by 1.76, and we have to take the cube of this guy. So cube, this term is 1.838. So the final answer is 399.099 into 629.703. Therefore, your heat flux comes out to be 461,889.664. This is your flux. And therefore, your H will be, you have to divide by delta T, right? Delta T is 15. So we need to divide it by 15. So you get H as 30792.644 watt per meter square Kelvin. And does it match with any option? Yeah, so this is your option A. Okay, so yeah, see, in boiling you'll get this type of questions only if you want numericals, because all the correlations are empirical, so they have to give you correlations. You just have to make sure that you don't commit any calculation mistake. If you do that, then you are lost, because that is the only thing where you can go wrong. So yeah, I think we have covered most of it. So do you have any other doubts or anything? If there are, then we can discuss. Otherwise, we'll stop for the day. Yeah. So if nothing is there, we'll stop for today, and see you next time.